Welcome back to the channel and welcome back to the series Networking to AWS. So we've been covering basics, and before we jump into today's topic, I want to start with a quick clarification from the last video. I got feedback and I'm really grateful and I appreciate the feedback that you guys have shared. I take it seriously because it's part of the learning journey that I am on. So thank you to all who reached out. But to the clarification I wanted to make, in the previous video, I discussed the TCP/IP model and in passing, the OSI model. This is a graphic of how TCP/IP maps to the OSI. While talking about the network access layer in TCP/IP, I mentioned it lies in layer 1. To clarify, in the TCP/IP model, that network access layer actually covers both layer 1, the physical layer, and layer 2, the data link layer in the OSI model. So, when I started explaining switching, I was referring to the layer 2 or the data link layer of the OSI model, which maps to layer 1 in the TCP/IP model. This is where switching really happens because it deals with MAC addresses and frames. I wanted to clear that up before we dive deeper today. So thank you again for the feedback and for catching that. In this video, we are going to zoom in on layer 2 switching. This is the foundation of how devices communicate in a local area network. By the end of this video, you'll understand key concepts like collision domains, broadcast domains, how switches use MAC addresses, VLANs, and why VLANs are so powerful. So, yeah, let's dive in. First, let's start with how devices communicate within the local segment. Every device in a network has something called a MAC address. Think of it like a unique fingerprint of a device network card. It's a 48-bit address that is split across 6 octets and is notated in hexadecimal. OUI, or Organizationally Unique Identifier, is the first half of a MAC address, representing the initial 6 hexadecimal characters, that is 24 bits, that identify the manufacturer or organization that created the network interface card or the NIC. The second half is a unique identifier assigned by the manufacturer to that specific device. So it's the work of the manufacturer to make sure that the last half is unique for every device. Switches use these MAC addresses to decide where to forward traffic. Here is how it works. When a device sends a frame, the switch looks at the source MAC address and records it in something called a MAC address table, together with the incoming port, that is the port in which the frame was received from. This process is known as learning, where the switch is learning the MAC addresses of the devices connected to it. This table tells the switch which devices is connected to which port. For the switch to forward data in the right destination, it checks for the destination MAC address in the MAC address table. Now, let's discuss some important terms in relation to forwarding data on a switch. The first one is unicast. This means one device is talking directly to another device. For instance, PC1 is sending a packet to PC3. The switch knows where the MAC address is since the entry exists in the MAC address table, so it just forwards the frame directly to that port. Unknown unicast. This is when the switch hasn't learned the destination yet, so it sends the frame to everyone. For example, PC2 is sending a packet to PC4. The switch doesn't know PC4's MAC address since the entry does not exist in the MAC address table. So it floods the frame out to all ports and sends it to everyone. Broadcasts. This is when one device wants to send a message to all devices in the broadcast domain. For example, when a device is looking for an IP address using DHCP or the address resolution process using ARP. We will discuss ARP in the next video, so you want to stick around to catch that. So subscribe so that you don't miss that video. Now, let's talk about collision domains and broadcast domains. A collision domain is a network segment where devices share the same channel, and if two devices send data at the same time, their packets collide and will not be delivered to the intended destination. This was a big issue in the days of hubs, where all devices shared one collision domains, but we no longer see much of hubs nowadays. Switches changed that. Each port on a switch is its own collision domain, which means there is no collision between devices on different ports, and devices can send and receive data simultaneously. On the other hand, we have broadcast domains. A broadcast domain is the group of devices that will receive a broadcast message sent from one device. In our case, if PC1 was to send a broadcast to all the devices, all the 4 PCs would be considered to be on the same broadcast domain, since they will all receive the data sent by PC1. By default, all devices connected to a switch are in the same broadcast domain. So to summarize, switches break collision domains into per-port segments, but broadcast domains remain the same across the entire switch, unless we use VLANs. This brings us to VLANs. A VLAN, or a virtual local area network, is a way to logically separate devices within the same physical switch. Think of it like creating multiple smaller networks inside one switch. Here is what VLANs do. By default, all devices on a switch can see each other's broadcast, as we discussed in the previous slides. But if you assign devices to different VLANs, their broadcast traffic stays within their own VLAN. So in our case, the green traffic is meant for VLAN 10 only, and blue traffic is meant for VLAN 20. Now, let's talk about port types in relation to VLANs. An access port connects end devices like PCs or printers. It carries traffic for only one VLAN, that is the VLAN that the end device belongs to. A trunk port is used between switches or between a switch and a router. It can carry traffic from multiple VLANs using something called tagging, which is usually 802.1q tagging. So, why do we use VLANs? Here are some of the main advantages in a table for you to visualize. The first one is segmentation. VLANs break a big broadcast domain into smaller ones. This reduces unnecessary traffic and improves network performance. Security. Devices in different VLANs can't directly to talk to each other unless traffic is routed between them. For example, you can separate the HR department from the finance department. Flexibility. Users can be grouped logically instead of physically. So in our analogy, even if finance staff sit on different floors, they can still be in the same VLAN. Efficient resources use. VLANs reduce wasted bandwidth by limiting who receives broadcast messages. Scalability. As your network grows, VLANs make it easier to add, remove, or restructure departments without physically rewiring the network. In short, VLANs give control, security, and efficiency. All right, let's wrap this up. Today we looked at how switches forward traffic, what unicast and non-unicast and broadcast mean, the difference between collision and broadcast domains, and how VLANs help us segment, secure, and scale our networks. In the next video, we'll move up to layer 3 routing and talk about ARP, routing between subnets, and how routers and layer 3 switches forward traffic across different networks. If you found this helpful, don't forget to like, subscribe, and share it with someone else learning networking. I'll see you in the next one. Bye-bye.